Imagine you have a huge code base written in C. It has been running for years, but hidden inside it could be memory safety bugs waiting to cause crashes, security vulnerabilities, or even critical exploits. Now imagine you want to move that code to Rust, a language designed to eliminate these problems while still delivering performance close to C. Sounds simple, right? Well, it turns out that translating C to Rust is much more than converting syntax. Rust follows a completely different philosophy for handling memory, ownership, and pointers. So the real question is, can existing C programs actually be translated into safe Rust? And if so, what is the best way to do it? In recent years, researchers have proposed automatic C to Rust translation techniques. Some rely on compiler analyses, while others use large language models. But despite all this progress, these tools still struggle. Static analysis-based approaches can safely convert only a small fraction of C pointers into Rust references, and even modern LLM-based systems successfully translate fewer than half of the relatively small C programs they are tested on. Instead of asking how can machines solve this problem, the authors of this paper asked a completely different question. How do humans solve it? Rather than building another translation tool, they conducted a user study. They asked students who were familiar with C and memory safety, but had very little experience with Rust, to manually translate real-world C programs into safe Rust. And the results were surprising. In this video, we'll explore the key lessons from this fascinating research paper. We'll see why humans currently outperform automated tools, what translation strategies they naturally adopt, and how these insights could shape the next generation of AI-powered and compiler-based C to Rust transpilers. Let's take a quick tour of how safe Rust works. The first and most important concept is ownership. Unlike C, where programmers manually allocate and free memory, every piece of data in Rust has exactly one owner at any point in time. When that owner goes out of scope, Rust automatically deallocates the memory. Because there is only one owner, memory is freed exactly once, preventing bugs like double free, which are unfortunately common in C. Ownership can also be transferred. If you pass an object to another function or assign it to another variable, the ownership moves to the new owner. The Rust compiler keeps track of this entire process at compile time. This ownership model is one of the main reasons Rust can provide memory safety without relying heavily on garbage collection. But if every object has only one owner, how do multiple parts of a program access the same data? That's where borrowing comes in. Instead of transferring ownership, Rust allows you to create references, also called borrows. These references temporarily access the data while the original owner still retains ownership. This gives Rust flexibility while still maintaining strict control over memory. Now, imagine borrowing an object after it has already been destroyed. That's exactly how use-after-free bugs happen in C. Rust solves this using lifetimes. The compiler tracks how long every variable and every reference remains valid. It guarantees that a borrowed reference can never outlive the object it points to. As a result, dangling pointers simply cannot exist in safe Rust. Now we come to one of Rust's most famous rules. Rust follows the principle called aliasing XOR mutability. The rule is surprisingly simple. You can have many immutable references, meaning multiple readers. Or you can have one mutable reference, meaning a single writer. But you can never have both at the same time. Why? Because if multiple references can modify the same object simultaneously, it's easy to create inconsistent state, dangling pointers, or data races. Rust prevents these problems before the program even runs. This compile time enforcement is one of the biggest differences between Rust and C. Of course, real-world programs sometimes genuinely need shared mutable data, especially in multi-threaded applications. Rust still supports these scenarios, but instead of allowing unrestricted mutable pointers like C, it uses special library types, such as reference-counted pointers, runtime borrow checking, and synchronization primitives. These introduce runtime checks only when absolutely necessary, allowing Rust to remain both safe and efficient. Rust also protects programs in two other important ways. First, it performs bounds checking on array and vector accesses. If a program tries to access memory outside the valid range, Rust stops the program instead of allowing undefined behavior. Second, Rust enforces strict type safety. unsafe pointer casts, and arbitrary reinterpretation of memory, which are common sources of bugs in C, are not allowed in safe Rust. All these rules work together to eliminate many of the memory vulnerabilities that developers have battled with in C for decades. Now that we understand Rust's safety model, let's look at how researchers have tried to automate C to Rust translation. Broadly speaking, there are two major approaches. The first approach relies on compiler and static analysis. Most tools perform the translation in two stages. First, they convert C code into unsafe Rust. This step is relatively straightforward because unsafe Rust allows raw pointers and bypasses many of Rust's safety rules. A well-known tool called C to Rust performs this line-by-line conversion very effectively. However, this is only half the battle. The difficult part is converting that unsafe Rust into fully safe Rust. Several research tools such as Laertes and Crown try to analyze ownership relationships and automatically replace raw pointers with safe Rust references. Unfortunately, these approaches still have significant limitations. For example, previous studies report that the vast majority of raw C pointers simply cannot be converted into safe Rust references automatically. This means that compiler-based techniques often leave large portions of the translated code inside unsafe blocks. The second approach uses large language models. Instead of relying purely on compiler analysis, LLMs generate Rust code directly. Their biggest strength is that they often produce code that looks much more natural and idiomatic. They can recommend appropriate Rust data structures, APIs, and coding patterns. But there's a catch. LLMs can also introduce subtle semantic mistakes. A translation may compile perfectly while behaving differently from the original C program. One of the latest systems, called Florine, shows this limitation clearly. Even with powerful models like GPT-4 and Claude, it successfully translates fewer than 20% of C programs larger than around 150 lines of code. So, despite impressive progress, today's automatic translators still struggle with relatively small real-world programs. Now that we understand why C to Rust translation is difficult and why existing automatic tools struggle, let's move on to the heart of this paper, the user study. The participants were undergraduate students enrolled in a computer security course. Although they already had experience with C programming and understood common memory safety problems like buffer overflows and dangling pointers, they had very little prior experience with Rust. Before beginning the project, they were given an introduction to Rust's ownership and borrowing system. The researchers selected 8 real-world C programs that represent the kind of low-level software where memory safety is especially important. 6 of these programs came from the BSD core utilities, while the remaining 2 were open-source libraries. Each student was randomly assigned 1 out of 8 real-world C programs collected from GitHub. Each program ranged from about 322 to 536 lines of code, making them realistic enough to expose the challenges of manual translation while still being manageable within the project timeline of 20 days. And unlike many controlled experiments, they were allowed to use any resources they wanted. They could search the web, consult documentation, use existing compiler-based translation tools like C to Rust, or even use LLMs to assist them. The goal was to understand the overall strategies humans naturally adopt when trying to solve the problem. The researchers defined 2 strict requirements. The first was memory safety. Every translated program had to be written entirely in safe Rust. Using Rust's unsafe keyword was completely forbidden. The second requirement was functional correctness. The Rust program needed to behave exactly like the original C implementation. Since most of these open-source C projects didn't already include comprehensive test suites, participants had another responsibility. They had to write their own tests and achieve at least 85% line coverage on the original C program. If the Rust translation produced the same outputs, return values, and external behavior as the original program across these tests, it was considered functionally correct. Interestingly, the researchers also asked participants to submit an early compilable version of their Rust translation before extensive testing began. This allowed them to study how the translations evolved during development. The results were surprisingly encouraging. Out of the 33 consenting participants, 31 produced final Rust programs that successfully compiled. Most of these translations achieved between 70% to 98% line coverage on the C program under their respective tests. 26 of the 31 translations passed tests that reach 85% coverage, and nearly all of them have coverage above 80%. Perhaps the most impressive result is that every single one of these final translations was written entirely in safe Rust. With these successful translations in hand, the researchers focused on answering 4 important questions. First, is there a set of common strategies that users used for successful translation? Second, how is the security performance trade-off in the Rust translation? Third, what are the common errors and correctness gaps in translated Rust programs? Finally, how do the state-of-the-art automatic C to Rust translation tools perform on the same task? Now we arrive at one of the most interesting parts of the paper. The researchers wanted to answer their first research question. What strategies do humans naturally use to translate C programs into safe Rust? To explain this, they begin with a simple example. Imagine you have a C program that manipulates strings using multiple character pointers pointing to the same memory. If you run this program through a popular translation tool like C to Rust, the generated Rust code looks almost identical to the original C program. Almost every statement has a direct Rust equivalent. But there's one major problem. The translated code is wrapped inside unsafe blocks. Why? Because it still relies on raw pointers, C library functions, and low-level memory manipulation, all things that safe Rust does not allow. You might think, why not simply remove the unsafe keyword? Unfortunately, it's not that simple. Even if we replace every raw pointer with Rust references, the program still won't compile. That's because the translated code violates Rust's borrowing rules, especially the aliasing XOR mutability principle we discussed earlier. In the example shown in the paper, 2 pointers need to stay alive simultaneously while one of them modifies the data. That's perfectly acceptable in C. But in safe Rust, this combination is illegal. Yet the participants still managed to translate these programs successfully. How? The answer lies in the strategies they naturally adopted. The first strategy is called semantic data type lifting. Instead of asking, how do I translate this pointer? Participants asked a much smarter question. What does this pointer actually represent? For example, many C programs use character pointers to represent strings. Rather than translating character into another pointer in Rust, participants simply replaced it with Rust's built-in string type. Once that happens, everything changes. Instead of manually iterating through characters with pointer arithmetic, they could use Rust's high-level string methods. Instead of calling C library functions, they could rely on Rust's standard library. The resulting Rust program often looked completely different from the original C implementation. And that's exactly the point. The participants weren't trying to preserve the original code structure. They were preserving the meaning of the program. Another fascinating observation is that there wasn't a single correct replacement. The same C pointer could be translated into several different Rust types depending on the situation. Across the 8 benchmark programs, participants used different Rust types. Changing the data type creates another challenge. If you've replaced a C pointer with a Rust string, you also have to replace all the C library functions that operate on that pointer. The researchers found 5 common strategies. The most common approach, used about 37% of the time, was a direct mapping. For example, a C library function would simply become a single Rust standard library method. Around 39% of API calls required something more creative. Instead of mapping to one function, participants combined multiple Rust methods and expressions to recreate the same behavior. Another 13% were handled by writing small helper functions that emulated the original C APIs. About 8% of the API calls disappeared entirely. And finally, only about 3% relied on third-party Rust libraries. The second major challenge comes from aliasing. In C, it's common to have several pointers referring to the same object. Rust, however, has much stricter borrowing rules. The obvious solution would be to use Rust's runtime reference counting types, which allow shared mutable access through runtime checks. But surprisingly, almost nobody did that. Instead, participants preferred solutions that satisfied Rust's compile time safety checks, avoiding extra runtime overhead. The researchers observed 2 dominant strategies. The first is called elision. Sometimes, after lifting the data into higher-level Rust types like string, many of the original C pointers simply become unnecessary. Instead of translating every pointer into a Rust reference, participants eliminated them altogether. The functionality that previously required multiple pointers was now handled naturally by Rust's built-in methods. This was by far the most popular strategy. It appeared in 25 out of the 31 successful translations. The second strategy is cloning. Sometimes the original C program needs one reference for reading while another simultaneously modifies the same data. Rust doesn't allow this because it violates the AXM rule. Instead of fighting the borrow checker, participants simply created a copy of the data. The original object remained read only. All modifications were applied to the clone copy. Later, the program continued using the modified version. By separating reads and writes into different objects, the Rust compiler was perfectly satisfied. This cloning strategy appeared in 13 different translations. Although cloning introduces additional memory usage, it avoids runtime borrow checking while keeping the code fully safe. One of the biggest reasons developers consider moving from C to Rust is the possibility of getting strong memory safety without giving up the performance advantages of systems programming. But there's an important distinction here. Not every Rust safety mechanism has the same cost. Some safety guarantees are enforced completely at compile time, meaning they introduce essentially zero runtime overhead. Others require runtime checks, which can affect performance. Across the 31 final Rust programs, the researchers identified 1,261 explicitly declared reference-like variables. These references were roughly divided into two groups. About 49.2% were owning references, meaning they were responsible for managing the lifetime of their underlying data. The remaining 50.8% were borrowing references, which temporarily access data owned somewhere else. Within the borrowing references, about 11.6% were mutable, while 39.2% were immutable. But the really interesting result comes when we look at when Rust checks their safety. Remember that temporal memory safety is about preventing problems such as use after free and dangling references. And this is where Rust performs extremely well. About 95.6% of owning references had their temporal safety enforced completely at compile time. For borrowing references, the number was even higher. 99.7% were statically checked. That means the Rust compiler was able to prove that these references would not outlive the objects they pointed to without requiring runtime checks. Of course, not everything can be checked statically. Some references in the translations required dynamic mechanisms. These included Rust types such as once-cell and mutex, which perform runtime checks in situations where compile time guarantees aren't sufficient. Interestingly, these dynamic references appeared predominantly around global variables. So the general pattern was local stack and heap data was mostly statically checked. Certain global or shared data may require runtime checks. There's another important distinction. While temporal safety was overwhelmingly handled statically, spatial safety was different. Spatial safety protects against accessing memory outside its valid boundaries. The researchers found that around 90.9% of borrowing references and 98.4% of owning references could involve runtime checks for spatial safety. This makes sense. The compiler may know that a reference is valid, but it doesn't always know at compile time whether a dynamically computed index is within the object's bounds. So, Rust can insert a runtime bounds check. If the program attempts an invalid access, Rust prevents the memory violation instead of silently allowing undefined behavior. The researchers also looked at nullable references. In C, a pointer can simply contain null, and the programmer is responsible for remembering to check it before dereferencing. Rust takes a much more explicit approach. A nullable value is typically represented using option T. This forces the programmer to acknowledge the possibility that the reference may not exist. In many situations, this can be implemented as a zero-cost abstraction. The programmer can also explicitly decide how the none case should be handled. If they don't, Rust provides mechanisms that perform runtime checks and can trigger a panic when an invalid value is encountered. In the user translations, about 63.1% of nullable accesses relied on these default checks, which may result in a runtime panic. The remaining 37% handled the nullable case explicitly without relying on a runtime abort. Another interesting category is dynamically sized types. In Rust, references to dynamically sized objects are often represented using what's known as a fat pointer. Unlike a simple C pointer, this reference can carry additional information needed to safely work with dynamically sized data. This can support runtime spatial checks while still providing a high-level and safe programming model. And these types were extremely common in the translations. For example, strings alone accounted for about 62.5% of the DST-related references, while buffers accounted for another 16.4%. But statistics about Rust types are only part of the story. The researchers also wanted to know whether the translations could actually eliminate known vulnerabilities in the original C programs. And the answer was yes. Two of the benchmarks, Shoko and URL parser, contained known memory safety vulnerabilities. The Shoko compression library contained a spatial memory vulnerability involving an array called packs. In the original C implementation, this could result in an out-of-bounds memory access. Every participant who translated this benchmark eliminated the original vulnerability. In the Rust versions, the corresponding access was protected by Rust's spatial safety mechanisms, causing the program to stop rather than allowing an invalid memory access. The URL parser benchmark provided an even more interesting example. The C implementation contained a use-after-free vulnerability. The problem occurred when an input string didn't remain alive long enough while being accessed by certain library functions. In C, this kind of lifetime relationship is largely the programmer's responsibility. But in Rust, the ownership and borrowing system makes this pattern illegal. The compiler can detect that the borrowed data would no longer be valid and reject the program. Interestingly, all participants dealing with this benchmark solved the problem by creating a copy of the input string so that the data could safely remain alive for as long as necessary. This is a perfect example of the strategy we discussed in the previous section. Now, moving on to performance comparison, but before that, let's address a problem. Remember, there were multiple Rust translations for each benchmark. So which Rust version should we compare against the C implementation? The researchers needed a fair way to choose. For each of the 8 C benchmarks, the researchers selected the Rust translation that was most similar in behavior to the original C program based on testing. They used test coverage as the primary criterion. The Rust translation with the highest coverage was selected. This resulted in exactly 8 Rust programs, one corresponding to each C benchmark. They reported performance only on test cases for which the Rust code and corresponding C have the same output and both exit normally. They also measured the execution time only between the entry and exit of the main function. This excluded differences in program loading and initialization that aren't directly related to the translated program's computation. To reduce the impact of noise, each program was executed repeatedly. The researchers performed 70 trials. They discarded the first 10 runs to allow hardware and operating system caches to warm up. They then removed the fastest and slowest 10 runs from the remaining measurements. Finally, they used the remaining runs to calculate the average execution time. Now comes the interesting part. The researchers compared the runtime of Rust against the corresponding C implementation. And the results were surprisingly positive. Out of the 8 benchmarks, the Rust translation was actually faster than C in 5 cases. For 6 out of the 8 benchmarks, the Rust versions had less than 10% performance overhead. Only 2 benchmarks showed more significant overhead. One had approximately 10% overhead, while another had around 40% overhead under the O3 optimization level. So, while there are cases where Rust is slower, the majority of the translated programs stayed remarkably close to the performance of their C counterparts. Some programming patterns are perfectly legal in C, but are considered unsafe in Rust. This doesn't mean Rust has no way to express the same functionality. Instead, Rust forces the programmer to use a safer abstraction. The researchers focus on 2 examples from their benchmarks: mutable globals and unions. Let's start with mutable global variables. In C, it's perfectly normal to declare a global variable that can be modified from different functions. But mutable globals can be dangerous. Because they exist for a very long time and can be accessed from many different parts of the program, they can become targets for attacks and sources of difficult-to-detect memory errors. They also conflict directly with Rust's aliasing XOR mutability principle. Imagine two different functions access the same global variable. Both functions could potentially obtain mutable references to that object whose lifetimes overlap. Rust doesn't want to allow this because it could lead to unsafe memory behavior. So, plain mutable global variables are not allowed in safe Rust. But what did the participants do when they encountered them? The researchers found three main strategies. The first and most popular strategy was surprisingly simple. Don't make the variable global anymore. Instead, participants identified where the global variable was actually used. They then created a local object whose lifetime covered exactly that region of the program. A reference to this object could then be passed into the functions that needed access to it. This has an important advantage. The object's lifetime becomes much more controlled. 19 participants moved global variables into locally referenced objects. And when there were multiple global variables, 11 participants grouped them together into a single struct. This is also a performance optimization. Instead of passing references to many different objects through the program, the functions can receive a single reference to the struct containing all of them. Sometimes moving a global into local state isn't practical. In those cases, participants could use Rust's dynamic reference mechanisms. For example, a global or thread local variable can be protected using abstractions such as refcell or mutex. These mechanisms allow the necessary shared access, but they introduce runtime checks. So this approach provides flexibility at the cost of some runtime overhead. Interestingly, only 3 participants chose this strategy. There was also a more specialized solution for global integers. Instead of using a dynamically checked mutable reference, participants could represent the variable using an atomic integer type. Atomic types provide special operations for reading and modifying values without requiring an ordinary mutable reference. This was used by 4 participants. So, once again, we see the same overall pattern. Instead of bypassing Rust's safety model, users adapted the representation of the data. The second interesting C pattern is the union. A C union allows multiple values of completely different types to occupy the same memory location. This is powerful, but dangerous. The programmer has to manually ensure that the value is being interpreted using the correct type. If they get it wrong, the result can be memory safety or type safety violations. Safe Rust, therefore, doesn't allow ordinary C-style union behavior in safe code. So once again, the question becomes, how do we express the same idea safely? The answer depends on why the C program was using the union in the first place. The first use case appeared in the Shoko compression library. The C code uses a union to access an integer as its underlying bytes. This technique is sometimes called type punning. The problem is that the result can depend on the machine's endianness. Participants translated this into Rust using safe conversion APIs such as. These APIs explicitly convert primitive values into byte arrays according to the desired byte order. And there's another nice property here. These conversions can be optimized away by the compiler, meaning they can effectively become zero-cost abstractions. Rust's conditional compilation mechanisms can also be used when the behavior needs to depend on the architecture's endianness. In the second use case, the C union was being used as a variant record, or what we'd typically call a sum type. Essentially, a value could represent one of several different alternatives. Rust has a natural abstraction for exactly this situation, the enum type. Instead of manually keeping track of which member of the union is currently active, Rust allows the programmer to define an enum with multiple variants. The compiler then forces the programmer to handle the different cases using a match statement. This provides static type checking and eliminates many of the risks associated with manually interpreting union memory. Rust enums are also memory efficient. Their memory requirements are related to the largest variant, much like how a C union reserves enough space for its largest member. Across the translations involving unions, 3 users use zero-cost safe Rust APIs for type conversion, 2 users translated unions into Rust enums, another 3 users implemented the functionality using structs and methods, although this could introduce more overhead. Again, we see a recurring theme throughout the paper. The participants weren't simply looking for a way to make the C code compile in Rust. They were looking for a safe Rust abstraction that matched the semantic purpose of the original C construct. Now, there's still one major question that needs to be addressed. Are these Rust programs actually functionally equivalent to the original C programs? Unfortunately, the answer is no. And this is where the paper uncovers what the authors call the gap in functional correctness. Remember that the participants were responsible for creating their own test cases. Most participants created tests covering more than 85% of the original C program, and their final Rust translations passed those tests. But high code coverage doesn't necessarily mean that you've tested every important behavior. There could still be unusual inputs, corner cases, or combinations of conditions that the participants never considered. So the researchers decided to perform an additional experiment. Instead of relying on human-written tests, they used automated fuzz testing. The researchers used AFL++, a popular fuzz testing framework. For each of the 8 C benchmarks, AFL++ generated test cases for 1 hour. The researchers then sampled up to 300 distinct tests for each benchmark. They ran these tests against both the original C program and the corresponding Rust translations. They ignored minor differences that weren't semantically important, such as differences in the exact formatting of error messages. The focus was on meaningful behavioral differences. Out of the 31 final Rust translations, not a single one was completely behaviorally equivalent to its original C program on the fuzz-generated tests. Across different benchmarks and translations, between 37% and 100% of the fuzz tests revealed some kind of behavioral difference. The average was around 68%. That's a substantial gap. So even though the participants' own tests suggested that their translations were correct, automated fuzzing uncovered many additional differences. The researchers noticed something else that was particularly interesting. Different people translating the same C program often made the same mistakes. For example, almost all translations of one benchmark failed on roughly the same set of tests. For Shoko, the translations failed on approximately 38% of the same tests. For the test benchmark, the number was around 50%. Why would different programmers independently make the same mistakes? The researchers investigated some of these common failures and found that they were often corner cases involving C library functions. These behaviors can be tedious to reproduce exactly in safe Rust. As a result, different participants independently missed the same edge cases. This is particularly useful information for future automated translators. The researchers divided the discrepancies into 3 major categories. The first category involves differences in input/output behavior and character encoding. C and Rust don't always treat strings and character data in exactly the same way. For example, many Rust string APIs assume UTF-8 encoding. If a C program accepts arbitrary byte sequences, translating that behavior directly into Rust string type can change the program's behavior. An invalid UTF-8 sequence might be rejected or cause a runtime failure in Rust, whereas the original C program might continue processing the raw bytes. So even though the Rust implementation is safer, it isn't necessarily behaviorally identical. The second category involves runtime safety checks. Suppose the original C program performs an invalid memory access. Rust doesn't allow that in safe code. Instead, a bounds check or null check may detect the problem and safely abort or panic. From a security perspective, this is an improvement. But from the perspective of strict functional equivalence, the behavior is different. The C program might continue or do something unpredictable, while the Rust program terminates safely. The third category is perhaps the most concerning. These are genuine logical differences. In these cases, both the C and Rust programs execute normally, but they produce different outputs or results. There's no memory safety violation involved. The translation is simply doing something different. And these logical discrepancies appeared across all of the translations. The researchers found that 27 out of the 31 translations behaved differently on more than half of the newly generated fuzz tests. That's a surprisingly high number. But it's important to interpret this result carefully. Not every difference represents a serious bug. Some differences are related to how Rust safely handles undefined behavior in the original C code. Others involve encoding assumptions that may not matter for the intended use of the application. And some are genuine logical errors. Let's take the encoding issue as an example. Suppose the original C program is designed to process arbitrary byte sequences. If a programmer translates that data into a Rust string, they're making a stronger assumption. Rust string expects valid UTF-8. If the application's real-world inputs are always valid UTF-8, then this difference may not matter. In fact, using string makes the Rust implementation much cleaner and safer. But if the application is supposed to support other encodings or arbitrary binary data, the translation needs to be more careful. The researchers also found an interesting difference in how participants handled safety violations. For 7 out of the 8 benchmarks, at least one participant produced a Rust translation that was completely panic-free. The URL parser benchmark provides a good example. 2 of its Rust translations avoided runtime safety aborts entirely. Other participants, however, allowed some operations to panic. The difference often came down to whether they used constructs such as option T unwrap. One programmer might explicitly handle the possibility that a value doesn't exist. Another might use unwrap and allow Rust to panic if the assumption is violated. Both approaches can be memory safe, but they have different external behavior. And this illustrates an important point. There can be multiple safe Rust translations of the same C program, and they don't necessarily behave identically on every edge case. Now that we have seen how human users approach C to Rust translation, the next question is, how well do existing automatic tools perform on the exact same task? The authors evaluate 4 state-of-the-art tools: Layerts, Crown, Florine, and Vert. The first 2 are compiler-based approaches, while the latter 2 use large language models. Let's start with Layerts and Crown. Both of these tools operate on top of C to Rust. Remember that C to Rust performs a relatively direct line-by-line translation from C into Rust, but the resulting code relies heavily on unsafe Rust. Layerts and Crown then attempt to take that unsafe Rust code and make it safer by converting raw pointers into Rust references. The problem is that the final step remains extremely challenging. The authors found that Layerts leaves approximately 95.3% of data references as unsafe raw pointers on average. Crown performs somewhat better in some cases, but safe Rust references still account for less than 3.1% of references on average across the benchmarks. And there's another important limitation. Layerts and Crown primarily work with relatively low-level Rust reference types. But remember what we saw in the user study. Human developers frequently lifted C pointers into much higher-level abstractions. These abstractions allow programmers to completely rethink how the original C code operates. The compiler-based tools, however, largely remain tied to the original pointer-oriented representation. C library calls create another major obstacle. When C to Rust encounters a C library function, the translated Rust code typically interacts with it through foreign function interfaces. For example, instead of replacing a C library operation with an idiomatic Rust API, the generated code may simply call the original C function. But FFI calls are inherently associated with unsafe Rust, and many C APIs themselves require raw pointers. So even if the surrounding Rust code becomes safer, these calls continue to pull the program back toward unsafe code. The next problem is perhaps even more fundamental: aliasing and lifetimes. Layerts and Crown attempt to lift pointers into Rust references while largely preserving the original control flow and data flow. But as we saw earlier, this can be impossible. A C program may have several pointers referring to the same object, with different reads and writes occurring throughout the program. Simply converting those pointers into Rust references can violate Rust's borrowing rules. So, do Layerts and Crown at least eliminate the memory safety vulnerabilities? Only partially. The benchmarks contain 3 known memory safety vulnerabilities. The compiler-based tools eliminate one of them, a read overflow involving a global array. That's because the translated Rust array receives automatic bounds checking. However, the other 2 vulnerabilities remain. One is spatial and the other is temporal. Both involve raw C pointers, and the tools are unable to lift those pointers into safe Rust references. So the final result is safer than the original C code in some respects, but it is not guaranteed to be fully memory safe. Now let's move to the more recent approach: large language models. The authors evaluate 2 state-of-the-art systems, Florine and Vert. These tools take a very different approach from compiler-based systems. Rather than simply preserving the structure of the original C program, LLM-based tools can generate more idiomatic Rust and make use of higher-level Rust abstractions. So, at first glance, LLMs seem much closer to the strategies used by human participants. But there's a major problem. They don't produce a complete runnable translation. Why? The main problem is program decomposition. Both tools assume that a large C program can be broken down into smaller components. Those individual components can then be translated and tested separately. This makes sense because today's LLMs tend to work much better on smaller pieces of code. But real-world C programs aren't always easy to decompose. Consider a simple call graph. Suppose function f calls function g. If we want to translate f independently, we also need g. Now imagine that main eventually calls almost every function in the program. The component containing main may therefore end up containing almost the entire program. At that point, we've lost the benefit of decomposition. The component is simply too large for the LLM-based repair process to handle effectively. There's an additional issue. Suppose we have two components. Both components contain G. If they are translated independently by an LLM, we can end up with two different Rust implementations of G. Now, we have to merge them back together. And this can result in conflicting type definitions and incompatible interfaces. The authors experimented with manually decomposing their benchmark programs into smaller components. They were able to obtain some compilable translations for individual components, but they still couldn't reliably merge everything back into one compilable program. But there's one more interesting question. Even if fully automatic LLM-based translation doesn't work, could LLMs still be useful as assistants to human developers? Remember that the participants in this study were allowed to use external tools, including LLMs, and almost all of them did. Out of the 33 participants, 31 reported trying LLMs during the translation process. Interestingly, 14 participants said that LLMs were helpful indirectly for tasks such as explaining the C code and suggesting Rust data types and APIs. However, direct code generation was much less successful. 20 out of 31 participants reported that LLM-generated code was error-prone and difficult to debug. And 2 participants eventually abandoned LLMs for direct translation altogether and chose to translate their programs manually. At this point, the authors have analyzed the translations created by their 33 participants in detail. But there is an important question. Are these observations actually generalizable to real-world Rust development? To investigate this, the authors conduct a post hoc analysis of a mature open-source Rust project called uutils. The goal of uutils is to provide compatibility with core utils and pass the same test suite. Unlike the participants in the user study, uutils is developed by experienced Rust programmers. So the authors examine 6 uutils programs and compare them with their corresponding C implementations. And surprisingly, many of the patterns observed in the user study appear here as well. Let's first look at the security-enhancing patterns we discussed earlier. In the user study, participants frequently avoided mutable global variables when translating C code to Rust. The same thing happens in uutils. The original C programs contain many global variables, an average of about 13.2 globals per program. But the corresponding Rust implementations almost completely avoid global variables. Instead, developers frequently group related state into structs and pass those objects around. The same pattern appears with C unions. Remember the idea of semantic data type lifting? The authors found very similar behavior in uutils. In fact, 83% of the Rust data types used in the uutils programs also appeared in the translations produced by the participants. The most common types in uutils include. The authors also investigate how uutils handles C library calls. Remember that the participants use several different strategies. The uutils project shows a very similar pattern. The authors examine 561 C library API calls and focus on the 10 most frequently used ones, which together account for about 53% of all the calls. They find that most of these C APIs can be expressed using safe Rust APIs or Rust expressions. Some functionality is implemented using third-party crates. For example, a C-Quote API is implemented using functionality from the Rust OS display crate. Interestingly, however, the authors don't find examples of the API emulation strategy that was observed in the user study. So there are some differences, but the broader pattern remains consistent. What about one of the hardest problems in C to Rust translation? In the user study, participants commonly dealt with aliasing using two strategies: reference elision and cloning. The authors investigate whether similar strategies appear in U-utils. Because the Rust implementation is often very different from the C implementation, directly matching corresponding code fragments is difficult. The authors manually inspect around 20 locations involving aliasing pointers in the C programs. They find 4 clear matching examples, and all 4 are examples of reference elision. One particularly interesting example comes from C split. A linked list implemented using pointers in C is represented using a vec in Rust. And this is a perfect example of semantic lifting. The authors also find many examples of cloning in U-utils. However, unlike the student translations, these clones are generally not specifically introduced to deal with aliased references. Now we arrive at another important finding. Earlier, the authors discovered that none of the 31 user translations was completely functionally equivalent to the original C program. The same phenomenon appears in U-utils. At the time of the study, U-utils passed roughly 80% of the GNU Core utils test suite. For 5 of the 6 programs examined, the repository itself reported known correctness gaps compared with GNU Core utils. One program, called Test, appeared to be much closer to functional equivalence because it passed the complete GNU test suite. But the authors went one step further. They performed differential fuzzing between the Rust and GNU-C versions of Test. They sampled 300 fuzz-generated test cases, and approximately 50.6% of those tests produced different behavior. After investigating those differences, the authors found that at least 23.6% of the tests exposed non-trivial logical differences. More specifically, about 2.3% produced different return codes, and around 21.3% produced semantically different error messages. Interestingly, they found no I/O encoding errors or runtime safety aborts in this particular experiment. There is another striking similarity. Earlier, we saw that successful user translations were often structurally very different from the original C programs. The authors find this phenomenon even more strongly in U-utils. They manually examined 142 C functions and 165 Rust functions across the 6 programs, and they could identify only 9 pairs of functions that were semantically similar, and even those were relatively small. Finally, let's look at the ultimate question. How much unsafe Rust does this mature project use? The answer is surprisingly little. Among the 6 Rust programs examined, only 1 program contains any unsafe Rust, and even there, it is just 1 line. This concludes our post hoc analysis. Note that it strengthens the paper's central conclusions. The participants in the original study were relatively inexperienced Rust users. Yet many of the strategies they independently discovered also appear in a mature Rust project maintained by experienced developers. So, after analyzing how human users translate C programs, comparing their strategies with automatic tools, and checking whether the same patterns appear in mature real-world Rust code, we can finally ask, what does all of this mean for the future of automatic C to Rust translation? The paper highlights a fundamental gap. Current automatic tools often take a very different approach from human developers. The authors argue that there is no single universally correct translation strategy. The same C program can be translated into multiple safe Rust programs. Each translation may satisfy memory safety, but differ in. Consider functional equivalence. Should a C to Rust translator preserve every possible behavior of the original C program? In some situations, attempting perfect equivalence may even work against the purpose of migrating the code to Rust in the first place. So, before automatic translation begins, we may need to define which behaviors must remain identical and which behaviors are allowed to change. The same applies to choosing Rust data types and APIs. Each choice comes with different trade-offs. This leads to a broader principle. Users should remain in control of policy decisions, while automatic tools focus on implementing those decisions. Once these policy decisions are clear, automatic systems can focus on searching for a valid translation. The paper identifies several promising directions. One major limitation of existing approaches is that they don't sufficiently model the rich ecosystem of Rust's standard library types, and AP is. Future tools need better understanding of mappings like. Without this semantic understanding, automatic translators may remain trapped in low-level pointer-based representations. The second challenge is decomposition. LLMs perform better on smaller pieces of code, but translating each function independently can create inconsistent translations that cannot be merged. So, future work needs to answer. How can a large C program be divided into smaller components that can be translated independently and still be assembled into one coherent Rust program? The authors suggest the idea of incremental migration. The third challenge is the final stage, making the translation completely correct. The study shows that translating most of a C program into safe Rust is feasible. The difficult part is identifying and fixing all the remaining semantic differences. The participants reported that debugging was often tedious. 10 users specifically mentioned difficulties in locating the root causes of semantic differences. 6 mentioned that certain library-related behaviors, such as regular expressions, were difficult to reproduce. And 14 participants said that LLMs struggled with generating long, correct programs. Interestingly, 4 participants said that they sometimes had to start a new LLM conversation with a clean context to get better results. So this suggests that LLMs may not be the complete solution by themselves. They need better support from testing, analysis, and verification tools. Based on their findings, the authors identify 3 particularly promising directions for program analysis. The first is analyzing mutable global variables. The second recommendation is particularly important. Instead of starting with, how do I convert this C pointer into a Rust reference? The tool should first ask, what does this object actually represent? The third direction is union translation. So, what is the ultimate lesson from this paper? The authors conducted a user study to understand how humans translate real-world C programs into safe Rust. And their findings show something important. Humans are often able to produce safe Rust translations where current state-of-the-art automatic tools struggle. And as this paper demonstrates, studying how humans approach the translation problem may provide some of the most valuable clues for building those future systems. And with that, we reach the end of this paper. If you found this video useful, don't forget to like it and subscribe to the channel. Thanks for watching, and I will see you in the next one.